In this video, we'll be taking a look at this particle kinematics problem. Here, we are given the position of a particle as a function of time in 3D. We need to find the acceleration and velocity at t equals 2 seconds. We also need to find the time when the particle stops moving in the x direction. We know that the derivative of position with respect to time gives velocity, and the derivative of velocity with respect to time gives acceleration. So we're going to use these ideas to solve this problem. So you might be wondering how to take the derivative of a vector valued function, because right here we're given the position of some particle as a function of time. So we're going to have to take the derivative. We'll start by just using the product rule, as you'll see in a second, where we essentially treat the function part here as a function of time and the I hat as terms. So if we go ahead and do the product rule, we get this. So I'll just start with the I hat one for example. So we get 6t plus 4, and then times I hat plus 3t squared plus 4t times I hat dot. Now you might be wondering, okay, well, I know this is pretty obvious, but what is I hat dot, right? I hat dot is essentially the time derivative of the I hat basis vector. And since we are working with a standard ijk basis in this example problem, where this is my I hat and this is my j hat, and then using the right hand rule, the k hat direction is out of the page, we know that essentially this basis is constant. It cannot change with respect to time. So what this means is that our I hat dot has to be 0, which means this entire part of the derivative is 0. This is also going to be the case for the derivative of j hat dot, and k hat dot. Now, it's important not to get this idea confused with other bases. For example, one common basis that will be used in the future is the polar basis, and the polar basis directly depends on your position. So I'll do this for example. Let's say that is some point. We'll let this be point O, the origin. We'll call this point P. Right here, point P, its polar basis depends on this position because the radial direction outward from the origin points that way. And sorry, I drew that wrong. The theta direction, this is E hat theta, sorry, and this is E hat R, is directly orthogonal to our E hat R direction in the positive right-hand rule way. So that is this direction. Now notice, let's let this be circular motion, for example, and let's let some time go by. And now this point is all the way over here. You'll notice our E hat R vector now points that way, while our new E hat theta vector points that way. So you can tell both of these vectors changed across that change in time, which means their basis vectors are non-zero. So we can write E hat R dot is not 0, E hat dot theta is not 0. Now this really just depends on the type of motion you have, but the main idea was just essentially just to get to know the fact that the derivative of a basis vector is not necessarily 0. Okay, so now knowing this, let's just go ahead and solve this problem. So we know the position, we already know that, so let's take the derivative to find velocity using what we already know about the derivative of basis vectors. We can just ignore it essentially. 6t plus 4 in the I hat direction plus 6t squared in the j hat. Now the derivative of negative cosine is going to be sine. So plus, but notice we have a 4 in here, so using the chain rule, it's going to be plus 4 sine of 4t, and this is in the k hat direction. Perfect, that's our velocity. Now we need acceleration. So let's go ahead and take the derivative of this. So the derivative of our I hat term is going to be just 6 I hat. The derivative of our j hat term is going to be 12t. And the derivative of our k hat term is going to be another 4 using the chain rule. So that's going to be 16. The derivative of sine is cosine of 4t k hat. All right, perfect. So now we know the velocity and acceleration both as functions of time. So all we need to do now is plug in t equals 2 to both of these to get the velocity and acceleration. So when we go ahead and do that, we can say that the velocity at t equals 2, so this is going to be 6 times 2, 12 plus 4, which is going to be 16. So we have 16 in the I hat direction. Then we have 2 squared, which is 4 times 6, which is 24 in the j hat. Now, I'm not really quite sure about sine of 8 radians off the top of my head, so I'm going to use my calculator. So that and then times 4, so we get for our k hat term 3.957 k hat. So that's our velocity it's equals to. Now let's do the same thing, but for our acceleration. So for our I hat term, it's just a constant 6, so 6 I hat. Now j hat is just going to be 12 times 2, 24 j hat. And now for our last term, same thing, I'm going to use my calculator. So cosine of 8 and times 16. It's actually negative 2.33 in the k hat direction. So this is our answer to part 1. Yeah, essentially just using these ideas of taking derivatives and also knowing how to use the derivatives of basis vectors and when they're 0 or not. Really helpful. So that's how you do part 1. So now let's go take a look at part 2. We want to find the time when the particle stops moving in the I hat direction. So since we only care about the motion in the x direction for this part, we only need to consider the I hat component. When the particle stops moving, this corresponds to a velocity of 0. Since we need to find when motion stops in the x direction, we only care about this term, like I said. So to find this time, we just essentially set the I hat component of velocity equal to 0. So we know from our previous derivative for our velocity calculation that the I hat component of velocity is just going to be 6t plus 4. And we're setting this equal to 0 because that's when motion in the I hat or x direction stops. So when we solve for this, we actually get that the time is negative 4 over 6 seconds. Now, this doesn't seem to make much sense just because we have negative time, but what this could mean is that from the reference point that we chose to use to start measuring our time, the point at which it wouldn't have been moving in the x direction would have been negative 4.6 or 4.6 seconds prior to that. So yeah, that's what that really means. It really just depends on when you start measuring something. So that's why it's negative. For most of your problems, you'll probably just end up having a positive value. But that is the main way that you would go about solving this problem. So yeah, I hope this was helpful. Thank you for watching.